Hello Game Jammers, welcome to Game Jam 2023. My name is Ricardo. I'm going to give you a very brief introduction to Unitary, a quantum gaming library. I apologize for the brevity and speed of this presentation, but this is many recordings in now and I'm trying to get it right. We're going to start off by installing Unitary from source on GitHub. Let's just start by validating that we have an installation that works. Excellent. So let's create a simple game that uses a 5x5 grid. We're going to model the grid as a set of quantum objects. So Unitary requires that you use an enum as a data structure for your quantum objects. So each square can either be empty or it can be full, so it'll hold a token or it holds nothing. Now let's just test and make sure that we can create a quantum object. We'll just have a throwaway variable name. We'll instantiate the quantum object class using a label. We'll just give it Z1, and we will pass in a state. Great. I got a little ahead of myself. Let's take a look at what we're actually building here. We're going to have a 5x5 board of squares. Each square is a quantum object, and that square is either empty or full. And if it's full, it'll have a token that we can move around, and if it's empty, well, there's not a whole lot going on there. We'll get started by building a data structure for our board. So we'll have a dictionary, and let's loop through and create this properly. So for each column, and we'll label our columns or our files A, B, C, D, and E, and then we'll have a number of rows 1 through 5, and rows 2 and 3 and 4 are empty, so we want to create a set of quantum objects in the empty state, and we're going to need a label for it, so we'll give it a label of the column and row, and we'll say the board at that column and row index is going to be a new quantum object with that label name in the empty state. Now let's do the same thing for the other two rows or the other two ranks, and we will create quantum objects in the full state because those have tokens. Oops. Oh, I spelled my variable name incorrectly. Okay. Good. Now we're going to create a quantum world which is going to hold our collection of quantum objects, and this is the object that's going to track the quantum state for us. Great. So let's just take a quick look and make sure that everything is as we expect it to be. We'll just take a look at the state of square A1. That's the square in the bottom left corner. And it should be in the empty, or it should be in the full state, sorry. if we look. And while we're at it, let's also take a look at it at an empty square. So C3 is the square in the center of the board, and it should be in the empty state. Okay, let's take a look, and the squares are as we expect them to be. Excellent. Okay, so the first quantum effect you can apply is a flip. So a flip will change the state from one value to another. So we know that C3 is empty. Let's flip its state from empty to full. And if we take a look, we can use the peak method on the quantum world, in this case our game board, to take a look at the classical state. We see that it is full on observation, whereas it was empty before. Great. Okay, well now let's use this flip effect to move a token from one square to another. So we'll start with A1 and we'll move the token in A1 to A2 by changing the state of square A1 to empty and the state of square A2 to full. When we run this, you'll see that we've changed the state of square 1 from full to empty and A2 from empty to full. You can use quantum effects like flip to implement your own moves in your own game, but Unitary also provides some convenience methods. For example, the move effect will, in practice, do the same thing as two flips on two different squares. Here we'll try it out on B1 and B2. So instead of flipping the state on each square, we'll just use the move effect to flip the states for us. And you can see that the move effect in practice had the same impact. Okay, so far this is pretty standard stuff, but as a quantum gaming library, we can start to do more interesting things. For example, we can create a superposition. So the split effect, for example, will enable us to take a token on one square and split it to two others. So in this case, we'll take the token on D1 and split it to C2 and E2. So again, we'll just make sure that we validate that the state is what we expect it to be before we split. And then we'll use the split effect. And the split effect takes a source and two targets. So D1 is our source. Then C2 and E2 will be our targets. So as we expected, there is a token on square 1 and nothing on C2 or E2 before we split. Let's think for a second about what we expect to see if we make a single observation. Of these squares in superposition. At any given time, there's a 50% probability that we'll find a token on C2 and a 50% probability that we'll find a token on E2. And every time we look, we might find the token on one square or the other. Unitary gives us the ability to do something slightly more interesting, and it's to look at squares a number of times. So let's just look at square C2, for example, but we'll look at it 100 times and see what we get. Oops. Oh. There we go. So you can see that sometimes we find it empty and sometimes we find it full. The quantum world gives you another tool that we can use as well, called the get histogram method. So rather than having to tally these up ourselves, we can just have the quantum world give us a histogram of the results. So let's do that. And you can see that we now have a probability distribution that each of those squares is in the 0 state or the 1 state, either being empty or holding a token. Okay. So this wouldn't be very interesting if our objects were only ever in a quantum state. So unitary gives you the ability to do a measurement or observe the classical state and fix that as part of the quantum world by using a pop method. So when we pop the state, that becomes a fixed part of the quantum world. We, in practice, collapse the quantum state. So now when we look at the histogram, we see that we are in the universe where the token is definitely on square C2. Okay, let's reset square C3 and do something a little more interesting, a little more quantum. So we know that in the classical world, objects cannot move through each other. So let's put the token on B5 on square B4 and try to move the token from A5 to C3. If you were dealing with classical state, you would have to code that manually, but because we are dealing with quantum objects, we need to have a way of controlling, of doing quantum control flow. And so we do that using the quantum if method. And the quantum if method is a controlled operation. So in this case, we're going to control on square B4, and we'll say if it's empty, then we'll apply the move effect. And if it's not, we won't. And because we've put a token on B4 with 100% probability, we know that if we try to do this move, it's not going to work. The token won't move from A5 to C3 through B4. And then we'll come back and we'll try this again, except we'll use our superposition power to put the token on B4 in superposition and observe what happens. So let's deal with the known case first. We'll just take a quick look, and we see that this square C3 is definitely empty. So let's try again. But first we want to move the token from B4 back to B5, and then we're going to split it to B4 and C4. So there's the move back. And let's split from B5 with 50% probability to B4 and 50% probability to C4. We'll just use this code again. So first let's run the code to do our move, and then we'll run the code to do our split. And now we see that the square on C3 appears to have a token about 50% of the time. So this was your whirlwind tour of Unitary. Hope you get some use out of it this weekend. I will try to be around in the Discord, and we'll drop some links to email lists and things like that where you can get some help. Again, everything is available on GitHub, including some documentation. Unitary is in an alpha state at the moment. We have some exciting things planned, like entanglement measures and supporting 4 states, which you can do now. It's just a little bit more technical. But yeah, look forward to seeing what you guys produce.